All right, so do you want to share your screen and then I'll briefly introduce myself, I'll introduce you, and then we'll just get started.
Sounds
And
good.
then for everybody else, Hannes will be here at some point. He's finishing up a seminar right now. Um, yeah, all right, let's get started. So I'm Ezra. I sometimes cover for Hannes, and today is one of those days. And today we have the pleasure of hearing from Eric on his paper, The Importance of Being Scalable, Improving the Speed and Accuracy of Neural Network Interatomic Potentials Across Chemical Domains. So with that, Eric, I'll hand it over to you and get started.
Oh, great. Thanks. Thanks for the introduction. I'm really excited to be here to share our work. This is joint work between me and my advisor, and we are at UC Berkeley. And feel free to interrupt me at any point if you have any questions. Yeah. So let's get started. So I'll give a brief background first. So I will introduce the idea of neural network interatomic potentials and something related to inductive bias and scaling. So, so we start with a really broad question. So how do we model physics? So uh, from a really long perspective, people have been using these first principle driven physical models. So essentially, people have been like express the physics as dynamical systems. For example, if you want to model like planet motion, you can have two dynamical systems, two first principles, like Newton's second law and law of gravitation, and you plug them in, and you have a system of ODEs. So if you solve the system of these, you get the motion of planets based on these principles. And so from so after we have quantum mechanics, we basically have all the first principle we need to describe the physical world. Like this is the famous saying by the Nobel laureate, and he says that like a large part of physics and the whole of chemistry can be explained by equations, but these equations are really hard to really complicated to be solvable. So they have a lot of dimensions, and it's really hard to solve them. So for different time and length scale, people have been developing different approximations of these true first principles. And here are like a brief overview of them. So basically, y-axis is the time scale and x-axis is the length scale. And based on different length and time scale, we have different principles that could model the physical systems. So like from top, we have turbulence models, like Navier-Stokes equations, some like for like continuum mechanics. And if you go down deeper, we have the StatMech equations, and then we have classical mechanics acting on atoms, and then we have the true accurate quantum mechanics, which is really complicated to solve. So for our purpose, we can go from bottom up. So firstly, we have the most accurate model, the Schrodinger equation from quantum mechanics that can be used to solve everything, but it has really a lot of variables. So it for a system with n electrons, it has 3n variables. So it's pretty much like unachievable to solve them computationally for a system other than one hydrogen atom. So people have been doing some approximations of Schrodinger equation. So basically, you have density functional theory. So this reduced from 3n variable to 3 variable. So basically, you model the probability density of the electrons at any given coordinate. And this is quite accurate. And but you have to find some exchange correlation functionals, which is also approximated. So it's not like 100% accurate, but if you have a good enough functional, it is as good as like a Schrodinger equation.
Wait, why are there only three variables here? Is this just like for a single atom or?
It's XYZ. So you model the like electron density over the entire XYZ coordinates. So you only have three
Oh, this is
variables.
like variables per. So I was just wondering because this complexity scales with O of n cubed, where n, I guess, presumably is the number of atoms in your system or electrons.
Oh,
I'm
so
I'm
this
sure it's
N
big.
is the electrons. Yeah.
Okay, so Schrodinger's equation would scale in like some polynomial of n, like n to the like some exponential thing, or what would be
Um,
the complexity of?
yeah, it's hard to say. So if you just don't think about like solving them, if you just want to store them, it's kind of impossible because you have three n variables and you have like if you take every combination of them, it's like for one, for example, like one common example is if you have only one ion atom, you have to take like the full internet to the space of full internet to store all of its Schrodinger equations. So it's really huge in order of like number like degree of freedom because you have to model each electron in 3D space.
I see, I see. All right, I don't want to. Sorry, I don't want to detour too much. I guess I'm just like qualitatively trying to understand why, like the number of variables per. My understanding is like in parentheses, it's like per unit in the system, like per atom or per electron. Why this scales with the size of the system, whereas DFT is just like, is this like you're measuring like the feature per atom is like scales with the like it's like interactions with other atoms or something like that?
Um, yeah, so this variable is like the input variable of your ODE. So like the variable of your ODE. Um, so you have to model 3n like a 3n equation for Schrodinger equation, but for DFT you only need model 3. So it's greatly reduced to like for the like underlying ODE.
Okay, all right. I don't want to kind of detour too much. Thanks for the explanation. Let's just keep going then.
Yeah, of course. Yeah, so yeah, for DFT, you also need to consider like the interaction between electrons. But for like classical molecular dynamics, you don't need to model electrons. So everything is on the level of atom, and you have empirical potentials. Yeah, I will describe this further. And so for this MD system, you don't have electrons, and you can think of atoms being modeled by balls connected by springs. And these springs are the bonds between the atoms. And these bonds are not broken or created during your like dynamics. And the time is discretized into like constant steps, and you solve them iteratively. Um, the so the force and also the like accelerations are on the atoms calculated from the energy. And the energy is calculated using a potential energy function or force field. And this potential energy function is an like empirical function that people like fit some parameters to get it work. Um, so this is a brief overview of how classical MD works. So in the start, you set some parameters such as time steps, like initial positions, initial velocity on each of your atom, and basically for each MD step, you first calculate the energy with the potential energy function, and this function is a function of the atom positions, and after you have that, you take a gradient over the the potential energy to get the forces. And so if you after you get the forces, you just use Newton's second law to get the accelerations, F equals ma, and then you input that like in current velocity and current acceleration, current like position to an integrator, and that integrator will go one time step further into the future and give you updated position and velocity. And basically, you repeat that again by just calculating the energy again. So you do this loop until you have your medsum and criteria. And after you end, you have a atom trajectory, and you can use that trajectory to calculate some the physical quantity of your MD simulation. So the key step is how do you calculate this potential energy? And it's the main bottleneck of MD in terms of computation efficiency and also accuracy. So like most classical force fields are roughly OM squared, where M is the number of atoms. And most of them are handcrafted, and it needs some small time step to be really accurate. For example, this is a really like popular force field called CHARM that is used to model like bio molecules. And you can see that like they have different terms for different like interactions. For example, you have contribution from the bonds, the angles, the dihedrals, and all of these. And these are all like these parameters are all handcrafted and fitted to make the MD work. So how do neural network or machine learning come to play? So basically, we want to use a machine learning algorithm to learn a potential energy function, and you replace that with your handcrafted empirical energy function. And we can so we want the accuracy, the potential energy function to be DFT level accuracy with MD level speed. So basically, we want the machine learning to learn from the DFT labels, which is, if you recall, is a higher level theory than MD, but still have the same speed. And if you want to express this as a machine learning problem, so your input is atom positions and properties, for example, atomic numbers, and people usually like convert these positions into radius graph to represent the structure. So the radius graph is constructed by, like, for example, if you have a center atom and a cutoff radius, and you calculate, you see like how many like atoms are within these within this radius cutoff. If they are inside this cutoff, you just connect them in the graph, and that's like how the graph is constructed. And the output is potential energy, which is a scalar over the whole system, and the force and per atom force. So this force is a 3D vector that is acting on each atom. And the training data comes from DFT calculations. So we want it to be the accuracy to be DFT level accuracy, and usually the architecture is graph neural networks with some different inductive biases. Yeah, and this is what we are going to talk next. So the inductive bias is a set of assumptions that model makes about the data. So for example, for graph convolutional neural networks, it has translational invariance. So like no matter how you translate your image, your output will like your output classifier will still be the same. For recurrent neural networks, it has an implicit temporal dependency of your like it makes assumption of that on your data. And for variational autoencoders, it assumes your like hidden latent representation is continuous and smooth. That can be represented by a really smooth distribution. And for graph neural networks, we have permutational invariance. So because for your neighbor, no matter how you order them, it will give the same results. So for neural network potentials, the big thing we are talking about is for inductive bias, it's geometry and symmetry. So basically, there are multiple ways to represent the same like atom structure. With, for example, if you just change the coordinate system, the 3D representation of atoms will change, but it will stay this but essentially you are representing the same object. So we want the model to predict the same output for different like representations, coordinate representations. So for example, if you think about rotational equivariance, so remember we predict a 3D vector for each atom in the structure. So this 3D vector is the forces. If you rotate the entire structure, atom structure, you want your output force to be rotated in the same way. So that is that is the symmetry and geometry like within these data. data. And so people have been trying to build some of these like symmetries into the model itself. However, we have the beta lesson of machine learning, which is a simple model with more data often outperforms complex model with less data. So for example, like convolution neural network used to work really well. However, nowadays, if you have a Bayesian transformer that is trained on a lot of data, the performance will be better than convolution neural networks. However, the Bayesian transformer doesn't have the like translational invariance built in. And there are some insights from other fields. For example, like handcrafted solutions are often quite limited because it's really hard to scale or generalize them like within your network. And data and compute often prompts human knowledge you embedded into the model. Okay, then let's talk about scaling. So this scaling, we are referring to the neural scaling law. So this scaling drives a lot of breakthroughs in modern machine learning or deep learning. For example, you have large language models and you have like AlphaFold, Bayesian transformers. So when we talk about neural scaling law, we often refer to these three plots. So these three things are key factors of scaling. So you have compute, dataset size, and number of parameters in your model. So if you control two of them and just increase one of them, the model will get better. So for example, if you like train your model longer, or you have you like give your model more data, or you increase the model size of your model, the performance will keep getting better. And in the domain of neural network potentials, if you want to find an analogy of these three factors, there are like a lot of big data sets coming up. For example, for at Meta, the fair chemistry team have been doing a lot of DFT calculations, like millions of samples, hundreds of million samples. And also we have the materials project that also is doing DFT on a lot of materials. And people have been throwing a lot of compute into train these models because they are quite like important. For example, Meta and NERSC at DOE. And there have been some efforts to build like large foundation models in the field. For example, the GMP foundation model and the MESOF or MES-MP foundation model that has quite a lot of parameters. However, the scalability of these models are often overlooked. So scalability is, in terms of scalability, we are talking about when you increase your model parameters, like how efficient can the model utilize your compute and your data. So if you refer to that plot, we want the slope of that data and compute plot to be have a better slope. And so nowadays, like NNIPs can be categorized into two main categories. Like one of them, like both of them are equivariant. So one of them is using group permutations to make the model equivariant. So basically, group permutation is like a way to represent rotation groups. And if you use that as your node feature, your node feature will be equivariant to rotations throughout. And however, it is really hard to maintain that equivariance, like the group permutation equivariance, and you have to use equivariant tensor products to maintain them, and they are really slow both in time and space. And another line of models that is using Cartesian coordinate as the node features, and these node features are invariant to rotations. However, you can do a small trick at the output head to make it equivariant. And these line of models often use handcrafted features to make it as input features. However, that is not flexible for scaling up as we know it. And so the motivation of this work is how to design a scalable architecture for neural network potentials. Okay. Yeah, so I think that's the background. Is there any questions? Let's see.
Yeah, feel free to put questions in the chat too if you don't want to unmute. Sometimes that's easier too.
Yep. Okay, let's continue. And so the first part of our work is investigation. So we try to investigate, like, do we really need high order representations in these group representation models? Like in group representations, you can there's like an order of representation. That is the L term here. So for the L term, it contributes heavily to the efficiency of your tensor product, and so this L is kind of the so you can think of these models as breaking out the directions of the edges to spherical harmonics, if you are familiar. And there's an order L of spherical harmonics that you can break it into. And so the first thing we think about is this L term really matter or not, or doesn't matter? And in the Equiformer paper, which is a state-of-art model with group representations, they do a they do a experiment with different L terms, and the L terms controls and however they didn't really control the number of parameters of between different L, and so we try to control the number of parameters between different L, and we L models, and we find that this L term doesn't really contribute much to the final performance. And this is very, very exciting and interesting, because like for a long time, people in this field have been thinking that why does this model work? It's because they have access to higher order informations of the direction, like edge directions, and they can represent that in higher L terms. However, we show that this doesn't really matter for for the large parameterized models, and we tried different ways to scale up these models, and we found that the attention component is the contributes most to the scaling, and this and because of that, this gives us a lot of insight when we build a model that the attention is key to scaling up and also to make the model more scalable. And we have an intuition for these high order symmetries that they could be seen as a kind of regularization. So when you have a small data set, these higher order symmetry could act as a regularization that can regularize your model to perform better. But when the data set is really large and you have a lot of when you have a lot of data, this could be acting as a constraint for scaling up the model. So so that's why we these really large models can perform decently with a relatively small L term.
Sorry, can you explain this plot a little bit more? The previous plot. So we see here mean squared error, and AT and SC indicate different types of models, right? So one is, I guess, equiformer, another maybe something more convolutional.
Yeah,
And I just can you just explain exactly what's the difference between the L6 and L4 alternatives between different columns? Because I understand what L6 and L4 mean in terms of spherical harmonics, but I want to understand what exactly is the difference between models.
Okay, sounds good. So for different L terms, it's just you'd go to different order of spherical harmonics in your model.
Yes,
And so yeah, essentially your node representation is a type L vector, and if you have higher order L, you have store more high frequency information in your node representations, and so in the Equiformer paper, they show that like if you increase L, you get better performance. And however, they didn't control the number of parameters when they compare different L. So these are all Equiformer models, just parameterized in different ways. So this is the L equals 6 is the baseline we are trying to compare to, and we scale up the Equiformer model using different ways. So you can scale up the attention and the spherical channels, which is like the hidden dimension of the model. Or you can just solely scale up the attention or solely scale up the spherical channels. And we found that during these between these comparisons, the attention, if you just scale up the attention model, the model gets better performance. And this is
Yeah, okay.
like another
I
experiment
see.
that you just further scale up the tension. Yeah.
And what does the last column mean?
I will
The
introduce that
OO?
later. Yeah.
Okay, I see. Okay, thank you. I got it.
Okay.
Looks like there's a question from Sudesh about the MA on slide 22. I think this is the previous slide.
Oh, yeah. So this is this is all forces. And we have a plot for energy in our paper, and it basically follows the same criteria. And actually, like energy have a better trend of like L, like lower order L works better. Yeah. But like forces is like what people most care about in the community. So that's what we show here. So force and energy MAE is like it's the standard metric to compare them in our field. So that's
Yeah,
why.
I understand it is a fair metric, like a standard metric, but wouldn't it be true to say that higher order terms may contribute disproportionately to some particular configurations of atoms, and you can essentially have higher variance. So the average energy can be good, but in some cases you can get like deviations from the physical plausibility, which these physics-inspired networks usually try to mimic closely.
Yeah. So like for the energy term, it's actually like a invariant term. So you only need L equals 0 to model that. And for force, you only need L equals 1 to model that. But like people discover if you like obey higher order like symmetries, the model tend to work better because of featureizations and others. Yeah.
Yeah, okay, thank you.
Okay. So this is the directional features. This is another thing we are investigating into. So the edges in this molecular graph have like real geometric information contained in them. So unlike like social networks, these edges have real geometric meanings. And so this could be a double-edged sword because you can have more information, but you have to obey their symmetries, or your representation could be really redundant. So for the group representation models, people like you just use a spherical harmonics expansion of the bound directions, and you take a tensor product between that with your node feature. So in this way, you like retain the equivariance of your node feature. For these Cartesian coordinate models, like people have been trying to using like really handcrafted heavy bound feature set, like mainly from also taking perturbations from like empirical MD. So you can model your dihedrals or your like angle, and put that into your model as input features. However, we think that like the first way is really like costly, and the second way is really like handcrafted and restricted. So what we are trying to do is we try to ask what is the simplest rotational invariant bound feature we can get, and that is the bound-oriented order parameter. So this BO comes from a StatMac paper, and it was used to like categorize the phase transition between in like crystal systems like in like previously, and we can take that as, however, it is also the simplest rotational invariant feature. So basically, for each atom, you took a look at its neighbor and the neighbor directions, they were bound directions, and you do a Cephalo harmonics expansion of that, and you take the average of its norm and also like average within each neighborhood, and then sum it over all the L terms. So basically, you can get a feature set that is characterizing the bound distribution over the neighborhood, and also retain some higher order, higher frequency, like information of the neighborhood. And yeah, so we try to plug this into the equiformer model, and so basically, when you do tensor products, you just do an order product, which that is like average weighted by this by a feature coming from this BO. And surprisingly, it gotten quite good performance compared to other models. However, it is R equals 0 model, which is an invariant model, but but with enough parameter, you can get similar performance with higher order models. And this begs the question of if do we really need equivariance, or do we like we can show that we don't really need higher order equivariance. And this shows that do we really need like just L equals 1 equivariance at all? Oh, let me see the chat.
I think people are basically asking how does these BO features fit in with the kind of overall philosophy of the paper, that kind of simpler is better if you scale. That's my understanding of the question. Feel free to kind of let me know if that wasn't exactly the intent.
Yeah, so basically, the overall philosophy of paper is like just make it simple, and however, you must give the model some kind of information to model the entire like atom structure. For example, if you don't give him like actual like angular information between each bond, or all the directional distribution of the neighborhood bonds, it won't it won't recognize some like structure, because your input is not sufficient to model like all the nearby geometries. So basically, you have to give him some notion of the neighborhood bond distribution for it to for it to be sufficiently model this like this geometry. And yeah, so
what do you think that the sort of takeaway is? Like if I look at the graph and I see that there are these special like kind of proposed BO alterations of the model that have slightly more parameters and don't perform, like what I guess what it's I'm trying to just summarize the questions here. It seems like people are just asking what's how we should interpret the models that rely on these BO features. Like if you just look at the graph, it seems like, oh, if I just do the more AT, I just pile all my parameters into this kind of into a tension, it seems to do better for fewer parameters.
yeah, so So basically, another thing to note is all of these models are trained to the same number of epochs, but they have like drastically different speed. So this L equals 6 is the slowest one, and if you go to L equals 4 or L equals 2, it will be much faster. So basically, all of these models are faster than L equals 2, and L equals 0 is like also faster than L equals 2. So basically, you gain a lot of efficiency when you go down the L term, and that's what we are trying to address. That because these models can utilize the compute much better than these like higher order models, so that we think these models are more scalable. In this way.
One question: do you use like CUDA kernels or just Python implementation?
So for this application, we didn't use it, but in our like in our like actual model, we did use some kernels and yeah, and try to speed it up.
So yeah, I guess the question is this difference in scaling of performance with a number of orders, rotational orders. Is it like irreducible, or is it mostly hardware dependent, and with efficient kernel can be perhaps different?
Oh, I see what you mean. So you are referring to the like some new works that like building kernels for tensor products, right?
Yeah, there are. I'm
Oh.
not even sure if they're so new, but there are some.
Oh yeah, sure. So yeah, these are not trained with the new kernels. So these are like taken directly from the like Equiformer code base. Yeah, but I think that's a good point. That like we noticed that these like there are people trying to optimize all of these tensor products, and yeah, that could be very very interested to compare again.
Okay, thank you.
So training with equivariance is, I don't think it's harder to train. It's just slower. So I have a like efficiency comparison later with between Equiformer and my model, and you can see that it's really like the speed is not really comparable. Yeah. Cool. Yeah, so this gives us some insight to build our model. So we want to use attention for scalability, which is like how efficient you can use your parameters. And we want to operate on scalar features, which is invariant. And we want to use data-driven feature for bound directions, like the BO features. And we aim the model to be scalable and efficient. So that's the model we propose, which is the efficiently scaled attention interatomic potential, or EScAIP for short. Yeah, because of time, I will skip the next part and go directly to the model, to our model design. Yeah, so this is the overview of our model. So basically, this is the overall architecture. It looks a lot like a transformer. So basically, you have attention and the feed forward, and after each block, we have a readout, which is like coming from the GemNet design, and so basically, after each block, we have a readout for edge feature and node feature, and they got concatenated in the end to send into the output block. And for the, yeah, I can go through them one by one. So for the input block, so that's, so these three are what what is the graph attribute we consider for our model. So we have the edge distance, and we use a RBF embedding, which is standard. So basically, you use a Gaussian smearing over your like distance, and we have an atomic number, and we also have the BO feature. So these are the only three thing we consider, and these are sufficient to model the entire geometry of the neighborhood. And basically, for the graph attention block, we take a graph attribute, and we take a node feature, and we concatenate them together to get a message, which is the edge level. And we use a multi-head self-attention block to just like process these edge features, message or edge features. And after we do that, we get the edge information and we aggregate them to get the node information. And the key operation is this multi-head self-attention. So basically, this is so basically we arrange our like message into a tensor like this. So we have a number of nodes by max number of neighbors by message size. And because our graph construction is the radius graph, and so basically the way we construct the graph, like usually in NNIPs, is you have a quite large radius, and you limit your max number of neighbor cutoff. So basically, you are creating a KNN graph, which is like k nearest neighbors, and this dimension is actually quite full, so it's not sparse. Not sparse like other like normal graphs because of the way we construct them, and so this is not so you don't need a lot of padding in this dimension, and you basically just send this whole message block directly to a self-attention, multi-head self-attention, where your number of nodes is the batch size, and your max number of neighbor is the sequence length. So basically, you are doing a self-attention over all the neighborhood, over all the neighborhood dimension, and you parallel them by the node. So in this way, you can exchange information within your local neighborhood, and it can also be paralleled pretty well. And after you do this multi-head self-attention, you aggregate them using a mask mean over the max neighbor dimension, and you get the node representations. And because
Hey, Eric, sorry, I don't mean to interrupt. I'm transferring back to Hannes. I actually have to run right now, but thank you so much. And I don't want to take any more time away, but I'm going to disappear from the Zoom, and that's the reason. Hannes is the host now, and I see his camera is on.
Thanks, Ezra. See you around.
See ya.
Cool. Thanks. Cool. Yeah, so because we arrange our like attention in this way, we can use some pre-built GPU kernels that are designed for like large language models, like directly here, because everything is organized this way, and it makes the model like very efficient and in terms of memory and speed. Okay, any questions for this version?
Not from my side.
Okay. Yeah, so finally we have the output block. So we break the force and energy prediction into two parts. And for the force prediction, we do actually something different than most of the models. We predict a force magnitude, which is a like a scalar for each force from the node readout, and we like predict a direction from the edge readout, and this direction is it's actually a n by 3 like sorry, not n, so number of edge by 3 vector, and that gets multiplied with the original like edge direction. So we so because the edge already have a unit direction when we build the graph, and we just like directly multiply this edge direction prediction with that original unit direction, and in this way the model is not equivariant because this transformation is not equivariant, but it gives some it makes the model better to optimize in this way, and we can show that we see that it gets better performance when you do it this way. And when you do for the energy prediction, we just do a prediction from the node readout and do an aggregation. Yep, and so in this way, the model is not equivariant at the output block. but it gives more flexibility when you do the force prediction. Yeah, so that's basically the architecture, and I will show some results of the experiments. So firstly, we have the catalyst systems. So we use the OC20 dataset, which has 170 million samples. And each sample contains about 70, on average 70 atoms for each system. And all of these labels are generated by DFT calculations. Like compare with equiformer. So if you compare this 150 million model with this 150 million model, we can see a 10 times speed up when we do inference, and also like about 7 times speed up when you do training, and also about 5 times the reduction in memory. And you can also see that the inference speed and the number of the inference memory is really scalable with the model size. So it doesn't require that much. It doesn't increase that much when you scale up the model. So this is also an efficiency comparison with other models, so our model is very. So the slope is very good because you use your scaling factor is way lower than equiformer, and we also use torch compile, which makes the error bar like nearly like visible here, because the inference between different batch is really small. And we also experiment on molecules. This is the SPICE dataset. Contains 1 million samples with different varieties of organic molecules. And so we compare it with the maze model. But to be honest, the maze model doesn't, so it's published, but it's not trained to train that good. So if you just train the model like in a better way, it will get better. But the comparison is also quite, so we basically outperform them on every split. And also the molecule like systems are much easier target than the catalyst systems. Yeah, just want to mention here. We also train it on the materials. So basically, this is the MPTrj dataset, which contains 1.6 million samples from the materials project. And we evaluate on the MPTrj discovery benchmark, which is you do some inference with the model to test its ability to like discover new materials. And we also outperform equiformer here. And the final thing that it could be that is interesting to brought up is the equivariance test. So as I said, the model is not equivariant by design. However, after training, you can basically show that it recovers the equivariance by itself. So how to access this is that we predict the forces on a atom on a atom system, I call it A, and we rotate the input system by a rotation matrix and predict the force again, call it B. And we compare the cosine similarity between B and the rotated A. And in this way, we can see if the direction change, like the change accordingly after your input change. And we can see that before training, they barely match up, but after training, it's basically get perfect like recovery of these directions like right after, which is quite interesting. And I think that shows that like the inductive bias of like rotation symmetry is quite easy to learn. And there are also other inductive bias that is not easy to learn. And yeah, I will elaborate on here. Okay, so conclusion, we think that this work follows the beta lesson, but it's actually a sweet lesson for the field, which is because our like our model requires way less compute and computation resources to train, that even like if like there's like even academic like compute budget could train, if you use this kind of method or follow this kind of philosophy, you can actually train train on really large data set even within academic budget. So that is very exciting, because like previous state-of-the-art models, like for example on OC20, is all trained on industry compute, because it's because Ecoformer and all other models are really TensorFlow-based models are really slow, but our model can like was able to train on the full OC20 dataset and get a really good performance solely from academic budget. And secondly, we think it's important that we give more credit to data generation, because like the chemical domain and chemical space is really like diverse and large, and it really requires a really comprehensive data set to be generated for these models to generalize to like unseen, for example, unseen domains. And we want this work because this work is a different flavor than like other neural network potentials, because like it's really focused on efficiency and scalable. So it's very different with like all the other works that trying to add more inductive bias into a model. We just let the model to learn basically everything that by itself. So we think that this can be another interesting direction for neural network potentials, that you just go efficient and scalable and let the model learn by itself. Yeah, and I think that's all of my presentation. Yeah, thank you. I will see some questions in the chat.
Yep. So one question in the chat is, how do you decide the radius of the graph on the max neighbors that you set in the attention layer?
Yeah, so basically the radius, we just make it really large. So basically we cover the whole system with a really large radius, and we try to find a max neighbor empirically by just testing. So I think it's we don't really need a really large number of neighbors to model the interactions actually. So basically we think that 20 to 30 is more than enough to model all of these systems.
Then your rotational equivariance test is very interesting. It seems to be the same result as AlphaFold 3, that rotational equivariance could be easy to learn with only data. Yeah, I guess not a question. Any comments?
Yeah, actually, yeah, this is actually like before the AlphaFold 3 is released. We trained that before it was released, and we were really interesting to see that these models have taken this direction. And yeah, we also find like there are different works on neural network potentials. For example, the ORB model, ORB model, that also doesn't use equivariant at all. And like there are like a direction shift in the field that people have been going to like just let the model train and don't add these equivariance.
Yeah, I mean, I think it's just having or the ability to have a more flexible architecture, and yeah, I guess you point out scalability as a major point. Is pretty often more important than building in equivariance. Okay, then any last words with which you want to end this?
Yeah, I'm really glad we have the opportunity to like share the work, and yeah, if you have any questions, just feel free to email me or ask me. Yeah.
All right, then thanks a lot, and see you around, and yeah, also see everyone else around. Bye, friends and Susan.
Yeah.
Thanks, Eric.
Yeah, thanks.